Okay. Are there any questions or comments about the lab? There seems to have been some confusion about DTFT.m. Dan, would you like to come and make an announcement regarding that? How we ended up sort of resolving that situation? First, maybe explain what the issue was, and then how you resolved it.
I guess the issue was whether or not you should have the DTFT file as something that's included in the lab. And, well, first of all, a lot of you guys who took 120 actually have it in your book from last semester. So that's one thing that you can use. Second of all, you can find it on the web. Third of all, you can come talk to me if you need any help with implementing it, which we talked about yesterday in discussion section and in office hours. So if anyone's having trouble, come talk to me and we can get it straightened out and you can have it and you'll have a copy of it. Okay?
Yeah, I mean, if I understand correctly, it's just making a DTFT routine. I don't think that's too much of a difficulty or an issue. So, did you have a lab session in the lab showing people? That was yesterday?
Yeah. And there'll be office hours again, lab session, whatever you want to call it, tomorrow.
And will it be on the first floor or in the
first floor, 199 Corey.
Okay, and you had left a note for them if they came to your office.
I left it on the website.
Okay, but let me just announce it then formally here, so that so Dan's office hours. Is it today or tomorrow?
Tomorrow.
Okay.
Tomorrow 3 to 5.
Tomorrow.
If anyone needs extra time too, I can come in some other time.
3 to 5 in 199 Corey, which is where the computers are. Okay. How many of you have finished Lab 1? How many of you have started Lab 1? Okay. All right, very good. So how long did it take you to... 6 hours. Okay. All right, any questions or comments? Okay, and for those of you who, Dan, we didn't end up putting the questions for Lab 1 on the web, did we? Scan it in? Yeah. Yeah. We can't really do that because of the copyright issues. So when you evaluate us at the end of the semester, don't say, not everything was on the web, the labs should have been on the web. You mean, I could have you buy another $90 book, and that way you have the questions, but I didn't really think it was worth it for everybody to spend $90 just for 3 or 4 lab assignments. So we can't put it on the web because you can't copy a book and put it on the web. It hurts the sales of whatever book that's there. So you should have picked up the handout from last time's lecture. If not, Rosita Alvarez, who is now in room 195M. All right. So one other thing is that I don't know if I announced this properly, but the course assistant, admin, Rosita Alvarez is now in 195M Corey, and she has the handout for labs, for the problems of Lab 1, plus all the graded homeworks, plus all the solutions. All the other goodies that you want is in her office. Yeah.
What is the title?
Don't know off the top of my head. It's a book in my office. Something like, I don't know, Experiment in Digital Signal Processing. It's got Oppenheim and Schaefer and 2 other authors. Yeah. I think for this course we have a total of no more than 4 lab assignments, and so. The second one of which, by the way, will be handed out on Friday and will be due next Friday. So I figured while you're in the lab mode, you might as well do more than one. Which just reminds me that, Dan, you should probably come to my office at the end of this lecture to straighten that out. So of the people in the room, how many have already used MATLAB in previous lives? In previous courses? Okay, just about everybody. Very good. Very good. Just wanted to reassure myself that you're not in unknown territory. So Any other questions or comments? All right, so what I'm going to talk about today is wrap up the coefficient quantization stuff from last lecture, and then move on to FIR filter design, and then after that IIR filter design. So what we talked about last time was the fact that if you have when you implement IIR filters, depending upon which realization you use, whether you use direct form 1, 2, cascade, or parallel, you get different quantization effects. In particular, what we found out, or what we saw both, was that in direct form 1 and 2, or because the roots of a polynomial are very sensitive to the coefficients, each coefficient quantization, and because what you actually implement, the coefficients, the numbers that you multiply are the coefficients of the numerator and the denominator polynomials. Because a slight change in those coefficients causes the roots of a polynomial to change, which could be either zeros or poles, the direct form 1 and 2 are very sensitive to coefficient quantization. And we showed that through an example off of Oppenheim and Schaefer. In particular, we talked about figure 640 in Oppenheim and Schaefer. Then we sort of ran out of time. On the other hand, when you're dealing with the cascade structure, because the coefficients that you use in the actual implementation, at least in the denominator, are the poles themselves, if you quantize a coefficient, you just change the position of that one pole, not all the poles. So think of it, if you have a 12th order polynomial and in direct form 1 or 2, when you change one coefficient, all the 12 poles change, all the 12 roots of the polynomial change. Whereas in cascade, when you quantize a coefficient, only the root corresponding to that will change, and therefore cascade in general is much more robust to effects of coefficient quantization. What I'm going to do now, before moving on to FIR filter design, is talk about FIR filters coefficient quantization. The results there are not nearly as spectacular or interesting, but I just thought I would show you one example of it, and then move on to talk about FIR filter design techniques. So we haven't really discussed what an optimum FIR filter design technique is, but we will in the next 4 or 5 lectures sometimes. But if you were to design an optimum FIR filter that has to satisfy a certain set of specifications, and I'll just talk about where can you zoom in as much as you can, where in the pass band you want the magnitude of the filter to be in this range, and in the stop band, which is omega between pi and 0.6 pi, this is a low pass filter, you want the magnitude of h to be smaller than 0.001. Then if you go through the Parkes-McClellan algorithm, which again I haven't talked about yet, we will in this class in like 4 lectures from now, you can design a filter that looks like this. So this is the magnitude of the frequency response in dB. So that's 0 dB. That means that 0 dB corresponds to 1, right? So it's 1 here, and then it goes down to like minus 60 dB or so down here, just like we want it to be. That's after crunching some numbers and getting the coefficients. And what I'm going to show now is what's called approximation. So as you saw in the specifications, we care about the pass band, which is the range between 0 and 0.4 pi, and stop band, which is 0.6 pi and pi. So when I come down here, you have between 0.6 pi and pi, and also between 0 and 0.4 pi. What I'm showing here is what's called the approximation error. This is deviation from 1 in the pass band, and deviation from 0 in the stop band. Okay, and so this is the ripple essentially in the pass band. This is the ripple in the stop band, and this is what that satisfies the specification, because remember we were allowed to have ripple of all the way to 1.01, 0.001 in the pass band, but in the stop band 0.001. So as you can see in the specs allowed us to have more of a ripple in the pass band than stop band. So here we go, we have more ripple in the pass band than the stop band, but that's not the point. This is the approximation error that you get if you use absolutely no quantization of the coefficients. And what I'm going to show you is what happens what happens to this approximation error as you keep quantizing coefficients. So what you see down here, which is more or less similar to what you had up there, is if you quantize the coefficients to 16 bits. So almost no degradation at all. What you see here is if you quantize the coefficients to 14 bits, almost no degradation. This is 13 bits. You're beginning to see a little bit of a degradation. And finally, this is with 8 bits. So the approximation error has just entirely disintegrated. And why is that? Well, it's supposed to be between look at this plot. It's supposed to be between minus 0.01 and 0.01 in the passband. And by the time you go to 8 bits quantization, it's exceeded to 0.03 and minus 0.02, so it's not satisfying the passband ripple. And then in the stop band, it was supposed to be between 0.001 and minus 0.001. And here, it's really exceeded. It's 0.02. It's like, 20 times bigger than it's supposed to be. So clearly 8-bit quantization is a bad idea. And you need to have more than that to keep the shape of the filter. You can also look at this thing in terms of the zeros of a FR low-pass filter. If you have an h of n, which is in finite length, you write h of z, which is a polynomial in z, which is a system function, and you factor that out, and that's the zeros of your FR filter. And if you were to plot that for the unquantized coefficient case, can you zoom in as much as possible? This is it. So these are the zero distribution that you get. And this is the zero distribution you get if you do 16-bit quantization. It's virtually indistinguishable from the unquantized case. This is what you get for 13-bit quantization, also virtually indistinguishable. And this is what you get when you do 8-bit quantization. All the zeros that used to be on the unit circle are now departed, and that pretty much explains why it is that the transfer function has just gone bizarre and gone to hell. So just to point out here in FIR filter design. There's not so much the issue of there's not so much the issue of what structure you use, but just the fact that if you use fewer than a certain number of quantization bits in your coefficient quantization, you sort of run into trouble. That's all I'm going to talk about at this point. Regarding quantization coefficients stuff, there's one other important issue when you talk about implementing these filters. There's one other important quantization issue that comes up that I haven't talked about, and that's a round-off. So besides the fact that your coefficients get quantized, when you add numbers up, there's round-off errors. If you multiply, or when you multiply an 8-bit number by another 8-bit number and you have to fit it into an 8-bit register, there's round-off errors introduced. And I will not talk about that right now in this point in the class. The reason being is that some knowledge of autocorrelation function and power spectral density is required. And the prerequisite for this course is not EE 126 or even 226, so I'm not really sure how many of you know about it, but I'm going to reserve this topic of round-off errors in filter implementations as something that, if time permits, to discuss at the end of the class as part of the advanced topics. I think it's an important issue. I think you guys should know about it and should worry about it, but I think because let me just do a quick show of hands just to confirm. How many of you know what an autocorrelation function is? Yeah. How many of you know what a power spectral density is? The same number. Yeah. I think because it's not a requirement for this course, I'm not surprised that some of you don't, and I don't want to cover it from scratch. So I'll reserve that topic as something to be discussed at the end of the semester. I might end up talking a little bit about later on about scaling issues in designing FIR in implementing IIR filters. So are there any questions or comments? Just pause for a second. Okay. Okay, so if there's no questions, I'm going to start talking about filter design, which is one of the central topics of this course. If you can zoom in. Okay, so to begin with, we can talk about two kinds of filters. One is FIR, and one is IIR. Okay, FIR filters have finitely many taps, and what I really mean by filter design is figuring out what the numerical value for those taps or those coefficients are. IIR filters, because of implementation issues, I've talked about this many times before. There's IIR filters with rational transfer function, and there's ones with not a rational transfer function, all the other ones. So what is a rational transfer function? Well, that means h of z, the system function, can be written as ratio of two polynomials, p of z over q of z. And primarily we'll be concerned about this class because they can be implemented with what? With difference equations, and we've spent a whole lot of time talking about that. And when I talk about FIR filter design for, I'm sorry, when I talk about filter design for IIR filters with rational transfer functions, what I mean is really the problem I'm talking about is determining the coefficients of these polynomials. So determine the coefficients of these polynomials. And in FIR filter design, I'm talking about determining the coefficients of the filter, or of h of n, if you will, or the taps of h of n. That's what we mean by filter design. So generally speaking, how do you go about designing a filter? Well, there's 3 steps that come into play. So the 3 steps of designing filters. Step 1 is you're given a set of specifications. This could come, we've talked about this before also, this could come from the particular application you're working on. If you're designing a tuner for your radio, you need to pass a certain range of frequencies and stop other range of frequencies. And so this is highly application dependent. And there's usually people who design an overall system, and then once they design the system, they come up with specs for each subsystem, and then everybody goes off and design their subsystem. And the way things usually work is that if every subcomponent or subsystem satisfies its specs, then the system engineer has assured that the overall system behaves as it is supposed to. So there's a specification that's highly application dependent, and we assume that we're given those set of specs. Then there is the design step, which I just talked about, which means determining all those coefficients, either the polynomial coefficients or h of n coefficients. And then there's the realization step that we already talked about a little bit. For example, you could have direct form 1, 2, cascade, or parallel. Okay. And then finally, there's an actual implementation. And the implementation, for example, could be just write a C program that does it on a PC or on a workstation, or it could be that you program a DSP chip, for example, a Analog Devices DSP chip or Motorola DSP chip, or it could be that you implemented on, I don't know, Xilinx FPGAs, or it could be that you end up designing an ASIC, which is very, very time consuming. As you move in this direction, it becomes easier to prototype and to implement. As you move in this direction, writing a C program on a PC is extremely easy, or you could even do something even easier than that is what? MATLAB, which is what you guys are doing, right? Which is not even a C program, because MATLAB even gives you the structures of how to write the signal or do other things. Anyway, so as you move up here in this direction, it's easier to implement. Certainly, programming a DSP chip is more difficult than programming a computer, but it's easier than building an ASIC. I must admit, I don't belong to the FPGA generation. These weren't in fashion when I was a student, so I have never personally programmed an FPGA, but I can, from what I hear or what I see, I would think that it's somewhere between these two things. Has anybody? The only thing I'm not 100% sure is the complexity of programming an FPGA versus a DSP chip. Has anybody done both to tell us how they compare? How many have done FPGA implementations in Scala? A whole lot of you, right? Pretty much everyone who took CS150, for example, right? Right. Anyway, so as you move down in this direction, the implementation becomes more difficult. On the other hand, the speed, once you implement the thing, the speed at which the thing runs becomes faster and faster, right? So I mean, a PC like that is a general purpose computer. It wasn't designed to be doing IR filters, and it's big and bulky and those other things. It's not just designed to do FIR filters or IR filters. But an ASIC, you can design a piece of an ASIC to be doing just FIR and IR, a piece of silicon that's just there doing FIR and IR filtering, which is probably part of a bigger system, and therefore you can get it to be to get much higher performance out of it than you would out of any of these other things. Okay. But of course, building an ASIC is a monumental task. You design it, then you have to do the layout, then you send the layout for fabrication, then 3 months later you get your chip back. You can do an FIR filter program on MATLAB in like 1 minute, essentially, whereas this is a matter of months and perhaps even a year to get the stuff done. So in this class, we don't worry about this last step of implementation. What I just talked about now is pretty much all the discussion we're going to have on the implementation. Are there any questions regarding the implementation issues? Have any of you built ASICs? I'll just do a quick show of hands there. Oh, okay. And was it a computational ASIC or analog? Was it and what did it do? Aha. Okay. And did it do equalization, for example? Okay, very good. And you? Uh-huh. So it was it had analog and digital. Pardon? Right. Right. So is it true? Is it the first statement to say that it takes weeks, not months, or maybe a year? Right. Just about a year. That's what I said. And there was one other hand. Yeah. What'd you build?
It was a 900 megahertz RF transceiver.
Uh-huh. So analog. And if I assume correctly, it was for wireless applications or something like that. Mm-hmm. And did it take about a year or two? Or more like?
Sort of I haven't tested it yet. So.
Oh, okay. Ongoing. Okay. So really building ASICs is a much more involved piece of action to do, but than these other things. So, but at the end, you get a small chip that does exactly what you want it to do, and it does it very fast. Actually, there's one intermediate thing in between these, and what's that? Programmable ASICs, I would call it. I mean, nowadays, I would say a lot of the ASICs are programmable anyway. Like, for example, you have an ASIC that does a whole bunch of... So let's say if I want to design an FIR filter, if it is non-programmable, I've designed it once, I determined all the coefficients, and boom, that ASIC that comes from fabrication only implements that one FIR filter with those set of coefficients that I designed. But a better idea is to do what's called programmable ASIC, where you download the coefficients to it. And so if tomorrow you woke up and the guy who designed the system changed his specs on you, and therefore you had to change your design of your filter, you can download this new set of coefficients into it. And now that I think about it, as my senior project when I was a student at Caltech, I built one of these programmable FIR filters. I think the TRW had just come up with these, I think, fast A to Ds and fast multiply adds and fast computation units, and you could sort of build programmable FIR filters. And then also when I was a student, there was this, I don't think you guys play much with what's called microprocessors, like the Motorola 68000, right? How many of you have heard? Yeah, you've played with it, right? But people don't program that so much, do they? Because in favor of what? Xilinx FPGAs and stuff like that. So that's a lot more fashionable, the FPGA stuff. But you would get a Motorola 68000 microprocessor chip. It would come actually in a board. And you could get to program it to do FIR filtering or IIR filtering. So it would involve programming up microprocessors. Also, when I was a student, the DSP chips weren't as available as they are today. Right now, I mean, who is the #1 DSP chip manufacturer in the world? TI. And what business do they sell most of their chips in? Cell phones. The cell phone industry is the single biggest consumer of DSP chips that are built worldwide. And what do these DSP chips do? Demodulate the incoming signal, bring it to baseband, decode it, to remove the FEC codes, do the Viterbi coding if there's Viterbi decoding, equalization. If your channel is bad, you want to adapt to the condition of the channel, which I guess we haven't talked about in this class. Possibly we could talk about it in an application. The #1 thing that you do is what? Your voice is being compressed, encoded in a particular encoding format. And does anybody know what those formats are? That's the name of the standard, but what's the name of the two audio formats of voice coding techniques? There's two. Yeah, go ahead. Anybody knows? There's two pieces to this cell phone industry. There's the CDMA camp, and then there's the GSM camp. And you all know what that means. So CDMA stands for Code Division Multiple Access, and the way it works is that the #1 problem in communicating over a set of a given bandwidth. Well, let me backtrack a little bit. When you're communicating, FCC has allocated different bands of frequencies to different applications, right? There's a band for military that we as civilians are not supposed to put any signal in that domain, any signal of significant energy in that domain. There's a band for I don't know, police. There's a band for fire guys. There's a band that got auctioned to be sold to cell phone operators, Verizon, Sprint, Singular, etc. Right? So here I am, Mr. Verizon. I either paid through my nose, or I bought, or I got lucky and won the lottery. You know, there was a while, like 8 or 9 years ago, they auctioned the Spectrum, and people bought tickets and won Spectrum. And then, like a dentist in Chicago won a hugest piece of Spectrum, and then he sold it to, I forgot, Nextel or some big carrier. Anyway, you buy Spectrum. Spectrum is a rare resource. It's just like having gold or having oil in your ground as a country. It's a rare resource, right? And then you get that Spectrum and say, I'm going to try to make as much money as I possibly can. I want to have 35 million subscribers, which is how many Verizon has now. Now, the question is, how do those 35 million subscribers share that spectrum, right? You all know about different frequency bands. So there's different methods of doing that, okay? One method is called code division multiple access, is that everybody has a different code, And based on that code, you generate a very low amplitude but wideband signal spreading over the entire range of the frequency band. Let's say Verizon's band is from frequency X to frequency Y. In a given, so there's two things. There's a spatial division. You've got a cell here, another cell here, another cell here. So in a given cell, which is a given region, all the users in that region share the spectrum by each having a different code. So I have a different code from you, and therefore, when my signal is received, this spread spectrum signal is received, I receive everybody's signal. But because I know what my code is, I do what's called matched filtering, and I can get a huge energy in my received signal and decode what was intended for me. But I can't decode what was intended for you, even though I received that same signal, because I don't know your code. Okay? So that's called code division multiple access. It's a spread spectrum technique. It was invented for the military like 30, 40 years ago, but this company Qualcomm in San Diego filed a bunch of patents, and now it makes chips for it. And of the two major carriers in the United States use what's called CDMA. Verizon and Sprint. Okay? Now, there's this different, and then there's carriers in Asia that also use CDMA, but let's not talk about global, let's just talk in the US. Then you got GSM, which is essentially a time division multiple access type thing, which means that you pick up the phone, you turn your cell phone on, you are given, in a particular frequency band, you're given a particular time slot. Okay, so then different users don't get mixed up with each other because they have their own time slot and their own frequency. So how do we get sidetracked to that? What was I talking about before all of these things? That's a challenge. Oh, the audio. So these two groups develop their own standards, and they just sort of keep moving forward. So the GSM or /TDMA camp uses a technique called AMR for audio. And don't ask me what AMR stands for. I've been using the acronym for the last 10 years. I never bothered to look it up. But it's a speech coding technique. And what bit rate do you think it occupies? What's the approximate bit rates? Yeah, somewhere between, I think it has 2 rates, right? So in all these situations, depending upon what your channel is doing, sometimes you're at the lowest possible rate, which is I think 7 kilobits or 7 or 8 or 9, something in that low, or you can have double the rate, 14 kilobits per second, if the channel is extremely good. Okay. On the other side, the CDMA side, because they're Qualcomm licensees, what kind of audio technique do they use? It's called QKELP. Q stands for Qualcomm, needless to say, and KELP stands for Code Excitation Linear Prediction. Thank you. And so what that does is it models the speech in a particular way and predicts the coefficients. And if there's time at the end of this class, I'll go over the different audio compression techniques these guys use. But the QKELP, again, the bit rates you can get at half bit rate as 7 kilobits, and then at full rate is 14 kilobits. Now these are meant to operate on voice, not audio, not music, for example. And if you pass music through them, they sound not too good. And so moving up the chain, if you wanted to process music, what kind of codec would you use? Yeah, MP3. MP3, why? Because it's free, not because it's the best technology, right? What's the best technology for audio coding today? AAC, which is the MPEG standard that comes after MP3. In any event, just again to calibrate you a little bit more about the available bandwidth, so that you know what we're talking about. So these two different camps, they sort of gradually keep improving their networks, right? So, for example, on the GSM side, they used to have. So who are the carriers in the GSM side in the United States? There's what? AT&T Wireless, Singular, T-Mobile, and VoiceStream. VoiceStream is not in the Bay Area, but some other parts of the country they're active. But if you think about it, so they started at a very rudimentary network. I think they advertised it or they marketed it under the name TDMA, and then they moved to GSM. And then the next thing that comes out, they call their next generation GPRS. And then the next generation after GPRS is EDGE. And then the next generation after EDGE, I forgot what it is, UTMS? UMTS, etc., etc. So they keep graduating the network to make it bigger and better and more bit rates and higher rates, etc. And then on the CDMA sides, they have the same parallel path. So they started off with what? IS-95, and then the next one after that is called 1X-RTT, and then the next one after that is EVDO. Okay, just so that you know what the status of things are. So Verizon, as we speak now, still uses IS-95. And what bit rates can you get through IS-95? Nominally, 14.4 kilobits per second. Really, more like 10. 14.4 includes, you know, the overhead, the packetization, this, that, a whole lot of things. You can never really get 14.4, more about 10 kilobits per second. Sprint, on the other hand, also uses CDMA, but they've graduated themselves to 1X-RTT, right? And what bit rates can you get out of that? Actually, these numbers, by the way, are sort of highly proprietary, and, well, I don't think they're proprietary. What I'm saying is my guesstimate. Okay, so don't hold me accountable if the thing is different. And when you ask them, they give you the answer, but they say, I wasn't the one who told you that. So I'm not the one who told you all these. Well, so Sprint 1X, what kind of bit rates do you get out of that? About 100 kilobits per second at burst rates. Burst meaning you just shove as fast as you can. Okay. How about AT&T Wireless and those other Singular and these other GSM guys? What kind of bit rates are they getting? Right now they're doing GSM, so very low bit rates. What bit rates are they getting now? At GSM is about 10 kilobits. Some of them have moved to GPRS. I forgot which ones actually. I know AT&T Wireless is moving to GPRS or EDGE at the end of this year or something like that. But they say they're gonna get something like 60 or 70 kilobits. Verizon says they're going to have 1X in February, and they say they're going to get 60 or 70 kilobits per second off of their 1X system when it comes up. Okay, and so if they do get, in fact, 60 or 70, or even in the Sprint's case, which is right now 100 kilobits per second, what kind of applications do you think people would use? I mean, human voice. You know, I don't think my voice is going to need more than 10 kilobits per second. I don't think there's that much. My voice or anybody's voice is not that rich in information to require 60 or 70 kilobits per second. So what are they intending these increased bit rates for? Yeah, video. Because nowadays you buy cell phones that have video cameras on it. All right, so you're in an exciting place and you want to take a video of whatever going on, or a still picture. How many of you, by the way, have a cell phone that's picture capable? Yeah, not me either. Don't look at me. Yeah. How many that are video capable? Probably none. Yeah. Anyway, so the bottom line is that the cell phone companies, after they went through the auction in the 90s, they paid a lot of money to buy this spectrum. They gambled. They said, we'll buy it. People will subscribe. We'll make a lot of money off off people, not American, just anywhere in the world. And what happened is, you know, the rate at which subscribers subscribe has saturated. Anybody who was gonna get a cell phone got a cell phone, and the people who don't have a cell phone really don't want to have a cell phone. Like my husband, he said, I don't want to be reachable by a cell phone. I know it exists. I don't want to touch that stuff, right? So there's a group of people who just don't want it. And so that's it. So these companies are now stuck. They paid a lot of money for their spectrum. So what are they doing? They're essentially providing you with new services like video and audio and games and all these other things to entice you to increase what's called their ARPU, average revenue per user, so that they make up for the money they paid for the spectrum through. They want to extract more money out of the existing subscribers because they just realized there's not going to be that many more subscribers. I mean, sure, I mean, I'm going to get a cell phone for my child as soon as his school allows him to take a cell phone, which they haven't yet, and maybe for my dog, but I can't get a cell phone for my refrigerator, for example, can I? No. I mean, there's only so many people in your family, and so So maybe, maybe for the birds in the yard or something, but that's it. There's not that big of a market. But just as now that we have talked about it, let's just do a quick show of how many people own cell phones. Quite a bit large enough. And how many don't? And the ones who don't, is it on purpose? Or is it you just thought it was too expensive? No, I won't look. Pardon? Anybody who's willing to answer. Pardon? Don't like, exactly. I think there's a distinct group of people who just don't want to be bought. I mean, they don't want to be reachable all the time with random people. Any other reasons for not having? Too expensive, maybe?
Like I'm at home before I have a land so
There's no need to.
like I don't want to come some lecture.
All right. Okay, well that's reasonable. There was a time, by the way, in 1998, 1999 time frame where even before the cell phones were all that fashionable, I would see that students will have cell phones, and in between classes, like between 11 and 11:10, they'll be calling their broker to buy and sell stocks between classes. And I thought that was an interesting use of cell phones. But at the same time, I had students coming to my office literally crying, saying they lost their shirt buying and selling stocks. I'm glad that those years are over and we all got sobered up. So that might have been a use for for a cell phone for you guys. But when this class ends, I don't see a lot of people calling their stockbrokers. So that's a good sign. All right, so so we got distracted into all of these. I hope you enjoyed this discussion. We got distracted into all of these, but these implementation issues, right? So where do most of the DSP chips in the world go to? They go to cell phones. And in particular, who's the #1 handset manufacturer in the world? Nokia. And who does Nokia buy their chips from? TI. And who decided this like just 2 days ago? Who's the second largest handset manufacturer in the world? Motorola. And what was the big news about them 2 days ago in the papers? They have decided to spin off the semiconductor part. They don't want to be in the chip business anymore because they feel they have to concentrate on their cell phone handset business and make their money off of handset. And what did Motorola use in their own phones? Their own ASICs. They were a vertically integrated company. They would make their own ASICs. They would put that same ASICs in the phone, and for some reason they're not succeeding, or they didn't succeed. I mean, I don't want to say bad things about Motorola, but I always thought the software was always lacking in the Motorola phones, and now if they're no longer a hardware company and they really concentrate on the handset, maybe the software and the user interface and the other issues sort of becomes more important. Let me just make one last comment in that in the other parts of the world, people perceive the cell phone industry is a lot more advanced than the U.S., both in Europe and in Asia. In Asia in particular, your cell phone is almost like a fashion statement. You have, the looks of it is very important. Also in the U.S., the looks is very important. So you could have a very good functional phone. I mean, I'll give you an example. There's a Toshiba AudioVox CDM9500 phone that Verizon introduced. And in my mind, I because of the various works that I do, I buy every time Verizon comes out with a phone, I buy it. Okay, not personally because of some activities I'm involved in. Not I buy it, I see it coming out. And this phone came out, and in my mind, it had the best display, it had the best video quality, it had the best audio quality, and after a month, it was discontinued. It didn't look good. People didn't buy. It's just the shape of it. It was just the shape was off. And it came out right after the Motorola T720 came out, and in my mind, it's a slightly better phone. But it got discontinued, No, they're not selling it anymore. And meanwhile, T720, which is a Motorola phone, it's a huge success, wild success. You know, I'm sure of this class, of this size, there'll be at least 5 or 10 people that have that one brand. So when you go home, take a look at it. Anyway, so there's a lot of, besides functionality of it, there's a lot of, you know, I mean, as an engineer, what do I look at? Oh, the display is good. Oh, the audio is great. But it didn't sell. It didn't look good. So there's a lot of other nebulous factors that affect what people end up using. Actually, most people, it seems like, want to have a phone for communication purposes. So what they care about is coverage. And what determines what kind of coverage you get? The carrier. Through what? How do they determine, how do they affect or influence coverage? By putting what? Base stations. So what happens is that if you want to cover a big geographic area, you sprinkle it with lots and lots of what's called base stations. So when I'm talking on the phone, I'm in a particular cell. They divide a big region into what's called cells. So my cell and a few other cells around it are all associated with one base station. So my signal goes to the base station, and then the base station routes that to another base station where the person I'm talking to is at, or maybe it's a landline. And then that base station then routes it to the other mobile user. And one of the major issues is what's called handoff. What does handoff mean? Is I move from one cell to another cell, and the designated base station for me now switches from this guy to another guy. And so to do a smooth transition from this base station being my designated base station to another guy is a hard problem. And all of this has to happen in what? What's the required delay? When you're having a conversation, FCC has mandated that when you have phone conversation, the delay between one end and the other end cannot exceed how many milliseconds? Pardon? No, it's less than that. It's 150. So when you talk from the east coast of U.S. to the west coast, even on landline, it can't exceed 150 milliseconds. The same thing with cell phones. So all of these, my signal going to the base station, from base station to the base station, from that base station down, all of that has to happen within 150 milliseconds, or else it doesn't sound like a conversation. It sounds like a one-way communication, like this lecture where I talk and you listen. Or I don't know how many of you have used, in the old days, satellite phones. Have you used, not satellite phones, have you communicated with like your relatives, let's say in Asia or India or China or Europe or whatever, via satellite phones? How many have experienced that personally? And do you feel the delay? Have you felt the delay? It's very you say something, you pause, and then they answer. No, it's really it affects. Exactly, when you watch TV, like what Peter Jennings is interviewing somebody in Baghdad. But you know, those guys use very high-end equipment. It has nothing to do with what you and I use, and yet there's delay. You're right. That's a good point. I mean, I always blamed, every time I see that happening, I always blame them. I said, look, you know, you're a big corporation. You could have afforded to have something slightly lower delay. But why is it that satellite has long delay? It goes all the way up to the satellite, which is up above the earth, and then it has to come down. That causes delay. And what system does the delay, what systems are what communication systems are satellites used most for, and for which delay doesn't matter? DirecTV. I don't know how many of you are subscribing to that. DirecTV, you're streaming MPEG, 200 channels worth of MPEG thing from up there down here, and it really doesn't matter if there's delay. Because it's a one-way thing, you're not interactively dealing with it. Although that's not exactly true. You are interactively dealing with it. In what way? When you switch the channel, again, I haven't used DirecTV in this country. I don't subscribe to those here. But when I'm on vacation, sometimes I see it in hotels. There's a pause before the next channel comes on. And why is that? There's a noticeable delay when the new channel comes on. When you hit on the remote control, you hit the channel plus. Why is that? Because it has to start buffering enough of the new channel before it starts displaying it. All right. Anyway, so speaking of all these sort of centralized issues, let me just do again a quick show of hand. If there is time at the end of the semester, how many of you would like to get into this speech coding stuff and learn about some of those things. Is there enough interest? Okay, there seems to be quite a good amount. So maybe that's. I mean, as we go through the course, I'll keep doing this show of hands, and then at the end we'll cover one of these topics if there's time in a little bit more depth. Okay, so a hell of a lot of these filters. The bottom line or the moral of the story is that a lot of these kind of filters get implemented in a lot of different applications, and so we don't really talk about implementation at this point, except that, again, one more time, if depending upon what your application is, there could be power requirements that dictate you to go from one to the other, and time requirements and all that. So what I'm going to talk about now, more than anything else, is FIR filter design, and in particular, I'm going to talk about two techniques for designing FIR filters. One of them is called Windows, and the other one is called optimum FIR filter design. I didn't talk about that. I showed you some optimum FIR filters and the result of coefficient quantization, but I didn't tell you what they are. Excuse me. Now, the Windows technique is sort of a quick and dirty way of designing a filter in a very short amount of time. The optimum FIR filter design involves a little bit more effort, but nowadays you got MATLAB, and this is a function in MATLAB that you just type in. I forgot what the name of the function is, optimum or Parkes-McClellan or some name like that, and you give it the specs, and boom, the filter comes right out. So it's so popular that it's so well spread and so well popular that it's not all that big of a deal to design optimum filters. But the reason I want to talk about the filter design techniques is the same reason as just because you know how to operate SPICE, you still need to know how circuits work, right? So the reason why is it that if you have SPICE, why do you have to ever know anything about circuits? Because otherwise the meaning, you won't understand the meaning of the things SPICE is telling you, you can't interact with it, and you don't know what SPICE did. Deep down you have to know, it's a difference between being a driver of a car and knowing what's under the hood, right? So the reason I'm going to talk about FIR filter design is because you understand the meaning of the result these MATLAB packages or other signal processing packages give you if you end up using them. So there's the window technique and there is the optimum filter. And I think in today's lecture and possibly on Fridays I'm going to concentrate on the window technique. So FIR filter design using Windows. Okay. So actually the basic concept is extremely straightforward. You start with the desired filter. Let's say you wanted to have an ideal low-pass filter. An ideal low-pass filter in the frequency domain is a box, right? And in the time domain, if you were to take the inverse Fourier transform of that, it ends up being what? A sink. So that's what I call an ideal filter. And unfortunately, a sink is an infinite extent. It's an IR filter with a non-rational transfer function. So what windowing technique does is say multiply it by a window so that it becomes a finite length sequence. The window you multiply it could be either a box. You just keep the first 100 coefficients and throw away everything else. Or it could be, a nice smooth window like Hamming, or it could be another window like Panning or Blackman or Kaiser or whatever your favorite window is. And thereby convert an infinite length, infinite duration sequence, an IR filter, into an FIR filter by just either truncating it or multiplying it by some window. That's all there is to it. Okay, so what the steps are is you start with a desired frequency response, H sub d of omega, and then you compute inverse discrete time Fourier transform of it, H sub d of omega, and you get H sub d of n. And then the last step is you multiply, you obtain h of n by multiplying h sub d of n by a function w of n, which we call a finite length window function. And all it's doing is making the duration of this become finite. So finite length window function. Okay, so so here is a small example of it. As a function of omega, I have h sub d of omega. Let's say goes from minus pi over 3 to pi over 3, and it's a rectangular type thing. Okay, and then the inverse Fourier transform of it is the sinc function. So it looks something like that. It's discrete, so that's why I'm putting these lines here. But it goes on all the way to infinity, and then let's say you multiply the w of n. Let's say is a rectangular window of duration 2n naught. So what you do, let's say it ends here. This is minus n naught, this is n naught. So this is h sub d of n multiplied by w of n. And in this case, I've picked w of n. Essentially, it's the truncated version of that. So from here to here, I've just truncated it. And if I truncate it, that corresponds to having a multiplied by window function that's a rectangular window. Not this rectangle, this rectangle. I multiply this by a rectangular window of duration and 2n naught. So that means I keep the first 2n naught coefficients and I throw everything else out. So that's a simple example of designing a low-pass filter. How about if I wanted to design a high-pass filter? Okay. So what we do as a function of omega, you have h sub d of omega. This is pi, this is minus pi, and you wanted to have a high-pass filter that went from pi minus omega c to pi plus omega c. Okay? So if you're looking between 0 and 2 pi, this is the region you look at. If you're looking between minus pi and pi, it's this and then that. It doesn't matter how the whole thing works. You can look at it from either minus pi to pi or 0 to 2 pi. So what are the steps that you want? So this is sort of an ideal high-pass filter, for example. And what we do is you compute inverse discrete time Fourier transform of this thing, h sub d of omega. And what do you end up getting? Well, here I've only shown you the magnitude of the ideal high-pass filter. I haven't shown you the phase of it. So what kind of phase should we assume? Well, because we're designing FIR filters, we got to decide whether we're doing type 1, type 2, type 3, or type 4. And then looking over our notes from last time, if you're doing a high-pass filter, what options do we have? You can do type 1. You can't do type 2. You can't do type 3. And you could do type 4. So coming back to this sheet here, for high pass, yeah, you can do type 1 and type 4. So for simplicity, let's just do type 1. Okay, so assume type 1.
You don't need to have linear phase, right?
We don't need to, but I'm imposing it. because, again, I'm assuming the application requires it. Okay. So if we do need linear phase, we're assuming type 1, in which case beta. So let me just write it down here. So assume type 1. In that case, beta is equal to 0. What's the number of taps? Number of taps is odd. Okay, so number of taps is odd, and alpha is n minus 1 over 2 as usual. So what do I end up getting if I make that assumption? Well, I can say that, well, we want to compute that, but based on these, what can I say about h of omega? Given that h of omega is here, well, I can say h of omega is some h sub m of omega times e to the minus j alpha omega, because I've let beta is equal to 0. And given that h of omega looks like this, and magnitude of, h sub d of omega, sorry. H sub d of omega looks something like that, because just because I assumed it's type 1, I also know magnitude of h sub d of omega looks like this. So what can I say but let's write down the expression for magnitude of h sub d of omega. Well, it's nothing but 1 in the range of omega between pi and pi minus omega c, and it's 0 otherwise. Okay, now given this magnitude and this general form for h sub d of omega, what can I say about h sub d of omega? Well, it's equal to what? E to the minus j alpha omega for omega between pi and pi minus omega c, and it's 0 otherwise. So why is it e to the minus j alpha omega? Is because I'm assuming linear phase. And I'm assuming type 1 where beta is equal to 0. So given that, now let's compute inverse DTFT of this. So inverse discrete time Fourier transform of h sub d of omega. What we get is 1 over 2 pi, pi minus omega c to pi plus omega c of e to the minus j alpha omega, e to the j omega n d omega. Okay, and then you get h sub d of n given by minus 1 to the power of n minus alpha. If you take the inverse transform of that, do the integration, all these things, pi over n minus alpha, sine of omega c times n minus alpha. So that's the ideal high pass filter. That's just the inverse transform of a filter like that. That's 1 in this range in magnitude, and in phase is e to the minus j alpha omega, where alpha is showing up here. And so if I now multiply, let's say, so this is of infinite duration. So this is of infinite duration. This is an IIR filter. It's another one of those IIR filter that doesn't have a rational transfer function. So it's of infinite duration, and if I now multiply it, step number 3, I want to multiply that by a finite length window. So multiply by a finite length window. And what do I end up getting? Well, what I get is, let's say the window is of duration 6. So what do I end up getting? Of duration 7, sorry. It's h sub d of n, h sub n, which is h sub d of n times the window w of n. I'm just truncating. Multiplying by a rectangular window, which is the same as truncating. So what do I get for n equals 7? 0, 1, 2, 3, 4, 5, 6. I get the value 0.1, 0, minus 0.3, 0.5, minus 0.3, 0, and 0.1. And is there any surprises here? No, because I assumed the type 1, I let beta equals 0, and type 1, I started with it, because I wanted to have a type 1, that means the number of filters n has to be odd, that's why I choose n equals 7. And a type 1 filter has 7 taps, and it has symmetry, right? So to begin with, my function here was symmetrical, and then I multiplied by a window function that was of length odd, so I preserve the symmetry in some sense, and I get a filter that looks like this. That's a 7-tap high-pass filter that approximates this infinite duration high-pass filter. What I'm trying to say here, maybe the point didn't come across very clearly, is that if you start with a linear phase ideal filter, h sub d of n, and if you multiply it by a symmetric window filter, what you end up getting is a symmetric linear phase filter. So the linear phase property is preserved. If you start with a linear phase filter, multiply by a symmetric window function, at the end you end up with a truncated h of n that's also linear phase. That's what I'm trying to say. So just let's see what's going on here. In time domain, effectively what's happening is that h of n got multiplied, h sub d of n got multiplied by w of n, which is the window, right? And what's happening in the frequency domain? Well, in the frequency domain, what we get is h sub d of omega gets convolved with the Fourier transform of the window function to get the Fourier transform of the resulting filter. Okay? I'm talking about discrete time Fourier transform. I don't think I'll have enough time to go over this diagram. I'll do that in the next lecture. But what we'll see is that, so let me just wrap up today's discussion with some very simple observation. And what's that observation? The observation is that if I wanted h sub d of omega to look, if I wanted h of omega to look as much as possible like h sub d of omega, what do I have to do? What should this w of omega look like? Huh? Impulse. Because I'm convolving this with that to get this, so if I want these two things to be like each other, I got to have w of omega be an impulse. And what does that mean about w of n? What kind of thing do I have to have? That means I have to have an infinitely long constant. So what that means is, but here, we did all of these things so that we don't have infinitely long things, right? We're doing all of that to have finitely long things. And so what it really means is that the longer I make the duration of the window in time function, this is w of n as a function of n, as I increase the, let's say I'm talking about rectangular window in this case. I can't even draw a rectangle. This is a rectangular. The longer I make the duration, it goes from minus n naught to n naught. The longer I make n naught, the longer the duration of this is, the narrower this w of omega becomes. So the width of this thing is, the width here is inversely proportional to n naught. So if I make n naught large, this becomes narrower, and therefore in the limit as n naught goes to infinity, this becomes like a delta, and h of omega becomes the same as h sub d of omega. But we're sort of, we don't want to have it infinite, so nevertheless it's good to know that one way of making h of omega to be close to the desired HD of omega is to have a long window. And that means have a large number of taps in your FIR filter. And that means more computation, more power. Your cell phone will get hotter, your ears will burn or something. Okay? So that's, and we'll talk about this trade-off in just a little bit more detail in the next lecture. And that's sort of one of the motivations that we move on to what's called optimum FIR filter design, because in optimum FIR filter design, given a set of specifications, you can be 100% sure, not even 99.9999, but 100% sure that you got the shortest number of taps you can ever get to satisfy those set of specs. And that's what the window design technique doesn't guarantee. But nevertheless, the window design technique is a simple and easy. And so if you don't have access to Parkes-McClellan algorithm on MATLAB, you can always do this, but you can't do the other one. It's a little bit more complicated. So we'll continue this discussion on Friday. Now, for the lab, yeah, let me first make a quick. It's a question from you. What do you want them to hand out? Go ahead. This mic will also work, but go ahead.
Okay. So for the lab, what I want to see is I want to see all the plots for all the questions that you have. I want to see the answers for anything that actually has a question in it also, and hand in the code that you use. You don't need to hand in the DTFT, but everything besides the DTFT, hand in.
Hard copy or email?
Hard copies. Okay? So hard copies on Friday.
Okay.
I'll post that too.
Excuse me. Question.